Imagine two different materials side by side, hooked to a power source. We push the electrical charges inside them with the exact same strength. In physics, we call this steady, even push, a uniform electric field. But look at the difference in how they react. The charges in the first material zip right through, like they are on an empty highway, while the charges in the second material are sluggish, struggling to make forward progress. If the electrical force pushing them is absolutely identical, why do the charges in these two materials move at such drastically different speeds? The answer comes down to a property called mobility. Mobility measures how responsive a material's charge carriers are to an electric field. Knowing the voltage of your battery is not enough to understand the resulting current. To predict how efficiently any material will actually carry electricity, we have to know its intrinsic mobility. Let's look at how we actually calculate this property. This equation shows the formal definition. Mobility, represented by the Greek letter mu, equals the magnitude of the drift velocity divided by the electric field. Drift velocity is simply the average speed that charge carriers travel through a conductor. The logic here is straightforward. If you crank up the electric field, the drift speed of the electrons increases proportionally. This graph shows exactly how that relationship works. As the electric field goes up, the drift speed goes up right along with it. Because they scale together, the actual value of mobility remains a constant property of the material itself. But there is a limitation to this macroscopic equation. It perfectly maps the math of what is happening on the outside, but tells us nothing about the physical reality causing it on the inside. To find out what actually controls resistance and mobility, we need to leave these top-level measurements behind and look closely at the quantum scale. Let's shrink down and follow a single electron inside a solid metal conductor. The inside of a metal is a dense grid of atoms. Our electron does not fly in a straight line. It is constantly accelerating and then violently crashing into heavy, fixed positive ions, losing its forward momentum every time. These crashes bring us to a critical concept called relaxation time, represented by the Greek letter tau. Relaxation time is the brief, average window of free flight an electron gets between those violent collisions. We rewrite drift velocity as the electron's charge times the electric field times tau divided by its mass. Plugging this back into our original fraction for mobility, the electric field sits on both top and bottom, so they cancel out completely. We are left with equation 3.25. Mobility equals the electron's charge times the relaxation time divided by its mass. The electric field from the battery is completely gone from the equation. A material's electrical mobility is an inescapable physical limit dictated solely by how heavy its particles are and how often they crash into things. We can apply this exact same microscopic math to entirely different states of matter. In solid metals like copper or gold, the current is carried purely by a sea of incredibly lightweight negative electrons. Compare that to ionized gases, like you would find in the upper atmosphere. Here, the current relies on a chaotic mix of those fast, tiny electrons and massive, slow-moving positive ions. Then there are liquid electrolytes. Electrolytes are conductive fluids, like the acid inside a car battery. In these, the electrical charge is carried by bulky positive and negative ions physically drifting past one another in a liquid space. This diagram displays the three environments side by side, showing the vastly different physical masses and shapes of their charge carriers. Applying our equation makes perfect sense. Increasing particle mass, or creating a denser environment, shortens free flight time, guaranteeing lower mobility. Whether you're engineering a chemical battery, lighting up a neon sign, or building a solid-state computer chip, mobility is the universal metric. It translates the sheer chaos of atomic pinball into the predictable, measurable electric currents that power our world.